Hey everybody. Today's topic, we're going to go through a pretty quick review of some rational number stuff that we talked about way back at the beginning of the year. So when you take a look at the top of your page, you'll kind of see a definition that I'm hoping we at least faintly remember. I'm not asking anybody to be able to recite the definition for what a rational number is, but after we've read it, then I'm hoping that you guys are like, hey, yeah, that sounds familiar. So I'll give you a moment to get that down on your page. But where we're going to go as you're doing that is we're going to start to look a little bit more at some of those rational numbers. And instead of just working with whole numbers or integers, we're going to start bringing back some of our fraction operations. So to do that, I want to spend a little bit of time today making sure that we're good with the different forms that numbers can take, as well as making sure that we're good with being able to reduce values to the simplest form possible. Okay, we should have that definition filled in at the top. You're going to come along with me a little bit as we work our way through our three different forms of numbers that can contain fractions. You guys take a look at that first form and you see 3/4. I'm hoping that we can put down the name of a fraction that looks like that as a proper fraction. Hopefully then you would remember that a fraction like 8/3, like what you see in the middle, would be something called an improper fraction. And I am somebody who has always had a problem with the formal name of an improper fraction because it makes it sound like that's not correct, it's improper. I need you to know that there is nothing wrong with leaving your answer as an improper fraction. That is fully reduced, it is fully simplified, it makes sense. So I know that we have an instinct that's been built into us over a couple of years where if we have an improper fraction, then we need to change it into a different number form. I'm telling you, you are perfect to leave it like that. Just make sure that we can tell the difference between a proper fraction and improper fraction. We know that our proper fraction has to always be less than 1. Because our top is a smaller number than the bottom. An improper fraction means that we're talking about values that are more than 1, the top being larger than the bottom. And then we can add in our third type of number form that contains a fraction, and you see on the end, that is a mixed number. It has a whole number and a fraction part. Okay. There's our three number forms, and then there's only one more thing that we need to make sure we're good on, and we've already talked about it this year. This is just where I want us to formally get it down. Make sure that you never, ever give me a fraction in the form of something like this, 7/6. Okay, I think we should be good that fraction is fully reduced. I just want us to be good that the fraction doesn't make sense. At the beginning of the year, I asked you guys to picture on your desk 6 pencils. And I asked you to divide those 6 pencils up into 2 groups. And then you guys would say, hey, how many pencils are in each group? And you would tell me 3. And I would go, good, now you know what division means. And we would have that little discussion about division. Well, now I want us to really see why that doesn't make sense. If I was to give you the number 6 divided by -2, I'm asking you to take 6 pencils and break them up into -2 groups. You can't even break them up into -1 group. So I'm hoping we see that denominator being a negative number doesn't make sense. So you have 2 options in that case. If you ever see a negative value on your denominator, then tell your reader that the value of your fraction is negative, so put the negative symbol on the fraction line, or you move that negative up onto the numerator. Now, for anybody who's like, you can do that? I'm going to say, sure. Isn't a positive divided by a negative the same thing as a negative divided by a positive? And so we're just changing the form of that fraction so that it makes sense. Okay, you have that down in your notes now formally, and then we should be good to move on. So let's take a look at the next problem. We take a look at question 1, and question 1 has asked us to convert, which is another word for change, to an improper or a mixed form. So in other words, wherever you're given an improper fraction, you change it to a mixed number. And wherever you see a mixed number, you change it to an improper fraction. Okay, I'm going to give you a moment to just try to work through, let's say, question A and B, and then we'll see how we do if we match up. So I want you to work through question A first. You're going to pause it, you're going to give it a shot, and then you can hit play and we'll see if we match up. Or if you're feeling brave enough, give both A and B a shot and we'll see if we match. Okay, pause it now. Okay, so we're back. So we take a look at 5/4, and hopefully we recognize that fraction line is just our division. And so I'm asking myself, how many times can I take a whole number of 4 out of 5? And I'm going to at least have one group of that, but not exactly one group. How many are left over? One more would get me up to 5. What are those size bits? They are fourths. So we've got 1 and 1/4. There's our conversion to a mixed form. So if that brought back a little bit of memory in terms of dealing with improper fractions, then I want you to pause the video now and give B a shot. Otherwise, we're coming along to check our solution. So in question B, we ask ourselves, how many times can we take a 5 out of 23? I can take at least 4 out because 4 times 5 is 20. That leaves me with 3 left over, and my size bits are 5. Okay, so hopefully those two went well, and we're feeling pretty good about it. I'm going to give us a chance then to pause the video now and give C, D, and E a shot at taking a mixed form number and changing it back into an improper. If you're a little iffy on it, then let's come along and we'll walk through C together. Okay, we take a look at C. And for a lot of us in our background, we probably have a little algorithm. We have a process that we've worked through to deal with mixed numbers to improper. We can say, since my size bits are 3, then I have my 3 times 4 gives me 12. And then I need to add on the extra on top. So for some of us, this might ring a bell where we go, hey, you take the number on the bottom, you multiply it by the big number and add on the top. And so in that case, I would now have 14. What size bits are we talking about? 3/3. I just want you to be a little wary of that. So let's make sure that we really understand what we're doing with that process. Okay, I want you to pause it now and finish off D and E. Okay, we're back. So we take a look at D, and I'm hoping that the most difficult part of D was having to multiply 9 times 7. So we've got our 9 times 7, that's going to give us 63. Add on the 2, gets me up to 65, and we're talking about ninths. Okay, why do I say be careful with that algorithm? I would bet right now that if we were going through this together in class, I'm going to have half of you that have E incorrect. I'm going to blindly follow that algorithm, which is I'm going to multiply my 4 times my -5, so that gives me a -20. I add on my top, so if I add on 3, then that gets me to -17/4. And I would bet that I have at least half of you that have -17/4 written on your page, and that is incorrect. So that's where I say be careful about blindly following that algorithm. I'm going to get rid of that just to remind ourselves that what that actually means is the value of 5 3/4 is negative. So when I follow that algorithm and I multiply, I have fourths, I multiply that by 5, I get 20, I add on the top. I'm multiplying that by the positive 5. So when I add on the top, I'm going to get 23/4, and that value is negative. Okay, be careful on that one. We're going to deal with some negative fractions this year, and that's something that you haven't had a whole lot of experience with in the past. And that's going to be one that might throw you a little bit of a curveball this year. So hopefully we're good. We're going to see it more often. Okay, let's jump into the next problem. Okay, so let's take a look at problem 2. Problem 2 asks you to write the fraction represented by the shaded part of each diagram. Then we're going to write 2 equivalent fractions. So the first thing that I want to address is I'm not trying to go back to grade 4 when you guys deal with this. I'm not asking you problem 2 because I think you need review on it. I want to talk to you about problem 2 because I think sometimes you go through the motions with it in the past. You know, we're all introduced to fractions, and I'm going to bet and say that most of you guys were introduced through fractions by like a teacher drawing you a pizza or a pie and breaking it up into slices. So you might look at these diagrams I've given you and go, oh my gosh, look at this. We're going back. Look, I understand what a fraction. But really what I want to get at is a little bit of the meaning behind it. So hang tight for a little bit as we walk through 2A. Write the fraction represented by the shaded part. I'd like you to pause the video and write one fraction for question 2A. Okay, pause it now. Okay, we're back. If I was a betting person, I would bet that you wrote down 4 out of 5. Because that's the easiest fraction to create for A. You see that that figure is broken up into 5 parts. 4 of them are shaded. There's our 4/5. What I want to get to in this is an important little bit of theory that I think sometimes we start to overlook. And we just start to look at fractions as, oh, these ugly numbers that have all this big process for us to work through. When I think if we can keep a couple ideas in our mind, we're going to find fractions aren't that bad. It's important for us to remember that what that 4 on top represents is my number of pieces. That's how many pieces would be shaded in this diagram. And what the 5 on the bottom represents is the size of the piece. That my division number, my denominator, just tells me how big of pieces we're working with. The number on top tells me how many of them I have. Now, why am I talking about that? Because you have to work with equivalent forms of fractions in so many different situations that sometimes we only ever think of those as reducing to lowest terms because that's something that my teacher made me do in the past. But instead, if we can become kind of freer with changing our forms of fractions, then you guys are going to find that fractions aren't that bad to work with. So I have now asked you to write 2 equivalent fractions. So I have one of them written. What I want is a second fraction form written. So you wrote down 4/5. I want you to pause it, and I want you to write down another form that would equal that diagram. Okay, pause it now. Okay, we're back. So my guess, and if I had to guess, and I would hope it would be this just for the sake of ease of drawing my diagram, that I would have a bunch of people that had 8/10 on their page. And maybe you thought of that as just, well, hey, I know I can have an equivalent fraction if whatever I do to the top, I do to the bottom. And so maybe we just said, hey, I'm going to multiply the top by 2 and I'm going to multiply the bottom by 2. That way, the value of my fraction has not changed. So we come in on 8/10. Good. 100% correct. 8/10 does equal 4/5. But why does it equal it? And so I want us to take a look back at the diagram, because really what we've done is we've decided that we are changing the size of the piece. So what does tenths represent in this diagram then? Well, really, that times by 2 meant double all of my individual pieces. Now, how did I do that? I took each piece and I divided it into 2. You can see that on my blue fraction, my divide by 10, I have an extra 2 down there. Well, now take a look at my number on the top. Why did my top number change? Because now I have a different number of pieces. You count up all my pieces. 1, 2, 3, 4, 5, 6, 7, 8. There is my numerator. So what I'm hoping we get when we take a look at that diagram, and I understand that it's a pretty simplified case, but all we're doing when we change the look of a fraction is we're just changing the size of the pieces, and we're changing the numbers of the pieces so that the value doesn't change. Okay, what am I talking about? Well, let's take a look at B. I want you to go through and I want you to create your first fraction. So pause it now, create the fraction. Okay, we're back. And so we take a look and you notice that you have 2 shaded in pieces out of 1, 2, 3, 4, 5, 6, 7, 8. 8 total pieces. So there is your 2 shaded is your number. 8 determines the size of the piece. Now what I want you to do is I want you to pause the video and I want you to create another equivalent fraction to that. Pause it now. Okay. Now, I could have had a bunch of people that, given what we did in A, you maybe said, hey, I'm going to double the top and double the bottom again. And go through and split up all of those shapes into 2 more shapes. We can see the times by 2 on the page. But I'm going to say we may have had a few other people who did something a little different. That is, maybe we reduce that fraction. And you said, hey, I have a 2 on the top and the bottom. I could divide both of those by 2 and get whole numbers. And so instead, you told me 1 over 4. Now, why is 1 over 4 the same value? Well, if you take a look at my diagram, if I break that diagram up in half, notice, divide by 2. I get 2 of the same diagrams. Each of those diagrams contains 4 shapes, 4 pieces, and 1 of them are shaded in. There's my 1/4. So all I did was I created the same diagram, a different diagram with the same value. That's all we're doing when we reduce a fraction. Changing the number of pieces because we changed the size of the piece. Okay, I'm hoping that gives us a little bit to go back to when we address how do we reduce fractions to lowest terms. Okay, let's jump into the next problem. Okay, so now you take a look at that problem, and I'm explicitly telling you, like I'm direct here, reduce each fraction to lowest terms. I want you to pause the video right now, and I want you to give all 3 of them a shot. And then we're going to come back and we're going to talk about your strategies that you used in trying to reduce each of those 3. Okay? Pause it now. Okay, so we're back. Let's take a look at the first fraction, 6 over 24. And this is one where I'm going to pick on you a little bit for your strategy to reduce. I think sometimes we have this idea in our mind where we go, okay, reducing to lowest terms means I try to find a number that goes in top and bottom. I try to find a number that goes into top and bottom. And that becomes the main focus for us. When we don't really hold on to, no, we want lowest terms. So when you take a look at 6 over 24, some of us go, hey, I know how to recognize, both those numbers are even. I know how to recognize that. So I know 2 goes into both of those. And so we divide top and bottom by 2. Then we take a peek at what we have. You see in pink, hey, 3 over 12. Wait a second, 3 goes into both of those. And so we divide top and bottom by 3. And I'm going to tell you that if that was our strategy to reduce fractions, we want a new strategy. Now, were we able to get down to 1/4? Yes. Is that fully reduced? Yes. Okay, but why did our strategy kind of fail us a little bit? It's because we got so focused on finding a number that goes into top and bottom evenly that we lost sight of lowest terms. I want to change the way you think about it. So I'm going to get rid of that and instead change the question you ask yourself. You have a fraction of 6 divided by 24. And we need to try to make sure that that is in lowest terms. The first question you should always be asking yourself is, does the smaller number divide into the bigger number evenly? You should always be asking yourself that. So you take a look at that fraction and we go, hey, I have 6 and I have 24. Does 6 go into 24 evenly? You're like, yes. So that's what I'm going to divide top and bottom by. I don't want to just find any number. And so since the fraction gave me 6, then I'm going to take a look and I'm going to see if 6 is the best one. So I can now go through, I can divide the top by 6, divide the bottom by 6, and go straight to my fully reduced fraction. Okay, let's take a look at B. I'm going to go down that decision-making tree. I see I have a fraction of 9 over 12. Then the first thing I ask myself, does the smaller number divide into the larger number evenly? No. Okay. Now I need to come up with a different strategy. So the second question I then move to is, do I know a number that goes into the top and the bottom evenly? And I'm hoping, because the numbers are relatively small, that we see 9 and 12 and we can go, okay, I know that 3 goes into both of those. So we divide the top by 3, we divide the bottom by 3. You never have to show me that. We could just do that reducing and we come in on 3/4. Okay. I think you have your strategies now. It's now just about being a little bit better with our strategy. So let's take a look at C. 35 over 21. First thing you ask, does 21 go into 35 evenly? Nope. So we need another way. So now we're starting to look for a number that goes into both 35 and 21 evenly. And here's where I'm going to say, don't random guess and check. That for a lot of us, because we've had access to a calculator for a while, this has become this like trial and error thing. Well, I don't know. Let me just try. 35 divided by 3. Nope, my calculator gave me a decimal, so that one doesn't work. How about divide by 4? Nope, that one doesn't work. How about divide? And we just keep going through this sequence all the time, hoping that we get values that work. Let's change our strategy. Take the smaller number. It doesn't always have to be the smaller number, but generally take the smaller number and think about numbers that multiply to give that. So you take a look at 21, and I made a comment to you last week about how much factor trees are of help to me when I problem solve. This is a great case to do a factor tree. Two numbers that multiply to give 21. 7 and 3. Well, I just found out the only two numbers that I'm going to try. So I take a peek. Does 3 go into 35 evenly? Nope. Okay. So I tried, does 7 go into 35 evenly? Yes. That is the one that works. If 7 didn't go in either, like we tried 3, it didn't work, and 7 didn't work either, then you know that that fraction is fully reduced. You don't waste your time trying 11 or 13 or 17. We don't even care. Because if it doesn't go into both numbers, then we don't care if it goes into one of them. So as soon as I factored 21 and got 7 and 3, I knew I only had two numbers to check, and that was good enough. We saw that 7 worked, so let's divide out our 7. So 35 divided by 7 is 5, and 21 divided by 7, we already know is 3. And there we go. Okay, we're going to spend some time today reducing the lowest terms. I want you to try that strategy as you go. Okay, different sort of thing to talk about. So, at the end of this note, I wanted to get down a couple things that maybe you've never been exposed to. Like maybe you've never had anybody kind of tell you a few little tricks, a few little patterns that could be really helpful when reducing. Maybe some of this stuff is stuff you've heard before, and it's a chance to just kind of put it all down in one spot. I want to go through a couple quick little hints on some patterns that can help you to figuring out what numbers go into other numbers evenly. So let's take a look at that first line. If we have a number that ends in 0, 2, 4, 6, or 8, I'm hoping we know that 2 would go into that number evenly. You'd say because they're all even numbers. The next line, I use this pattern all the time, but I find that there's so few students who've ever heard of it before. If the sum of the digits is divisible by 3, then 3 is a factor of that larger number. Now, what does that mean? Well, if I was to throw out a number like 7, 2, 6, 726. Notice the way I said it, 726. So when I see 726, if I do a quick 7 plus 2 plus 6, and I add up the digits, then I add up those digits and I get 15. Then I ask myself, does 3 go into 15? Yes. Then that means that 3 goes into 726. That can be a really helpful tool to have when you're trying to figure out how to reduce a fraction. So watch out for that sum of digits trick. It works a lot. Okay, take a look at the last one. This is one that I use every once in a while. It's not like my 2 or my 3. But 4 is a factor of numbers if the last two digits are divisible by 4. So if I have a number like, let's stick with the 700s, it makes it nice and big, 712, then if I just look at the last two digits, 12. Well, does 4 go into 12 evenly? Yes. Then that means 4 goes into 712 evenly. Sometimes people make the mistake of focusing on it being an even number. To give you another example, 722. I may have a lot of students who go, hey, but I think 4 goes into that. Well, if you do a quick check, my last two digits would be 22, and 22 is not in my 4 times table. So that one can be helpful for you to be able to work through and go a little quicker to a value of 4. I think most people are fine with if the number ends in 5 or 0, then we know that 5 is a factor. Okay, you take a look at those little hints, tricks, hints, something to look for. I think those things can help, and those are the ones that I use most often. The last one that I use an awful lot, and this is one that I am putting a star beside because it might be the most used one that I have, is I know that if 6 goes into a number, then it has to be divisible by 2 or, sorry, that shouldn't say or, that should say and 3. Now, why do I say that one's the one I use most often? Because it uses 2 smaller tricks, and 2 tricks that I know well and that are easy to use. Let's go back to that number 726. We went through and we added up the digits. Now, if I was trying to look to see, does 6 go into 726? So if 726 was a part of a fraction that I had and I had to try to reduce, am I going to waste my time to try 6? Well, the first thing I look at, it's an even number. So yes, 2 goes in. Then I do a quick sum of the digits and I go 7 plus 2 is 9, 9 plus 6 is 15. 3 goes into 15 evenly. Well, then that means 3 goes in as well. And if 2 goes in and 3 goes in, then 2 and 3 come together to make 6, then 6 goes in. That could be a nice way to jump over and reduce a fraction faster. Those ones that I just put in pink, those are the ones that I use most often. My big starred one on 6, I use that one all the time. Okay, the last 3 are ones that are probably, at least 2 of the 3 are less known, but they can be helpful. And I don't know, if you have a really good memory and you spend a lot of time practicing this stuff, they can be useful. That what we end up having is 8 is a factor if the last 3 digits are divisible by 8. Kind of similar to our 4, but we have to take in an extra digit. 9 is a factor if the sum of the digits are divisible by 9. Shouldn't really surprise us that much that the 9 and 3 rules would be very similar, considering 9 is made up of 2 3s. But shouldn't surprise us. And then the one that I hope everybody knows, 10 is a factor if our number ends in 0. Okay, it might be nice to have that with you to use as you move forward. But the faster we can get away from using that as a bit of a cheat sheet, kind of a decision-making list, to where we just know some of those, I think you guys are going to find that very helpful. Okay, your job now, jump in, get some practice. Good luck.